and thanks for coming. So yeah, I'll be excited to tell you a little bit about, well, really motivate the collection of work that my group has been working on in the past few years, related to stochastic gradient methods for solving constrained problems. And today I'm going to try to motivate why we think about constrained problems as being useful and appropriate for certain supervised learning problems in particular. So I'll motivate that, and then eventually I will tell you about some of the more recent things. I'll tell you about various extensions we've done so far, but I'll tell you about a particular project that's going to be coming out probably in the next few days, about using momentum within these kinds of algorithms, which of course people know is very effective, and we've found the same thing also in a constrained context. All right, so this is basically building off of a lot of work that's come out of a group over the past few years, and these are a collection of students and faculty and postdocs who have come out of Lehigh. So I just want to very briefly mention their names. There's Albert Barajas, Lingjun Guo, Xin Zhang, Zara Kati, Slava Convergence, Suyun Lu, Mike O'Neill, Christian, I'm not going to get his last name correct, so I'll skip that. Dana Robinson, Chi Wang, Laura Zebian, and Bao Yu Zhou and Yonglong Zhu. I'll tell you about the particular projects of theirs coming up in a second. Okay, so the first one I'm mainly going to be focusing on in the motivation is a paper we wrote a few years ago with Albert, Daniel, and Bao Yu, just basically introducing the idea of doing constrained optimization with stochastic gradient-based methods, and sort of the foundational theory from there. And then eventually I'll tell you about this work with Chi, Christian, Daniel, and Yonglong. It should be Yonglong's name there. Sorry. Okay, so here we go. Let's do a little bit of motivation. So, I mean, I think this is something that everybody is recognizing now, but I just want to like formalize it to sort of just put into context what we're doing. I mean, sort of traditionally in optimization, the way we think about things is that we have some kind of information about a problem setting or a scope that we're dealing with. And then data comes along to give us a particular instance in order to give us a decision. So for example, if you think about it, you've got a graph, you have some kind of graph structure. You want to do, say, like shortest paths. You have a graph structure. You design your algorithm based on just having that structure. And then once you get a particular instance, like the edge weights, you can solve the problem and get your decision from there. Similarly, with some kind of optimal control type setting, right? In each case, this information that the problem structure is being defined first. And then from there, you're going to get the data to actually create an instance to solve the problem. But these days, we're kind of doing it in a different way, right? I mean, with a lot of settings, we're just taking data, assuming that we can learn directly from the data, not necessarily imposing a lot of prior knowledge, just the data is somehow going to reveal to us when we train some kind of prediction model based on this data that we can make new decisions, right? So in this case, we start off with data, we train a model based on that, and then the new data comes along in order to make a particular decision or a prediction, right? In this case, these models can be pretty generic, depending on the setting that we're dealing with. And so the question is, how should we incorporate knowledge into this? How should we incorporate further information about the setting that we're dealing with based on the certain task we're trying to learn for? So let me just, I think probably everybody's familiar if you've taken some machine learning class about supervised learning, but let me just introduce this as a way, the notation and everything, in order to introduce where the constraints that I'm thinking about are coming from and what kind of structure that they have. So, and generally what we're trying to do here is we're trying to learn some kind of prediction function from some family P, just so that anytime you're given an input vector, you're going to produce this, or evaluate this prediction function on that input to give you some kind of output. Generally speaking, we would parameterize this. So these parameters, for example, could be the weights of a neural network, something like that. That's what we choose to optimize over. In order to do supervised learning, we're going to assume we have a bunch of inputs and output pairs, right? So we've got this predictions now parameterized by the vector x, but we're going to be comparing those to some known outputs in these A's corresponding to the BJ's. In order to measure the discrepancy, in order to do the training, we're going to introduce the loss function, right? So this is a standard type of supervised learning problem, trying to do our best, find the parameters x that will give us the best relationship between inputs and outputs that we have previously, and then we're going to take that prediction function on any kind of new inputs that we see. But the question is, how do we impose some additional knowledge? Now, one kind of additional knowledge or structure would be something that, like, my classical thing would be I don't know, maybe sparsity, right? So we want to come up with a simple model. So we'd introduce, for example, some regularization function, maybe L1. This is how we're sort of not just going to say we're going to learn from the data, but we're trying to impose something in additionally on top of that, right? So it could be that we just want the model to be simple. We would impose a simple regularizer in that case. But what if we wanted to impose information in another way, right? Rather than just some straightforward regularizer, something maybe related to the prediction functions P, something we know that the prediction should satisfy, and things like that. Well, one way to handle this would be to just change this prediction function into something that is incorporating knowledge in other ways. So, for example, you can think about, like, if this is a neural network, you might be embedding something in different layers of the neural network. Like certain layer might be solving an optimization problem or solving a system of equations because you know that essentially your mapping from your inputs to outputs should have some sort of relationship on either layer-wise or so on. So you could change the prediction function P, or you can just assume that you have some sophisticated enough neural network with various types of attention mechanisms, whatever, that you don't need to do anything else. Like this might be enough. The problem is that this is not necessarily going to capture exactly what you want. You're not really doing anything specific for your task. You're just handling it maybe in some kind of generic way. So maybe there's alternative approaches. The ones that we wanted to explore would be more like settings like this, where, okay, you have your data fitting term, but you might also be including an additional term, maybe with some weight there. I didn't put it, but maybe with some weight there, where you're trying to include some additional information. So now we can start to think about a case where maybe we know that our prediction function P should satisfy some ODE. So like you're thinking about a physics-informed learning type setting, which I'll talk a little more about later. We know, for example, that this prediction function should conserve mass or something like that. So you can include that into basically a residual term in your objective function, right? And you can include some weight on this, basically say, yes, I want to fit the data, but I also want to impose this additional behavior on my prediction function P. And your data could be, these A tildes and B tildes could be a subset of your original data on the first term, or some other values, in general. The challenge here, though, is that now we have these two terms, and if we're going to apply our algorithms to it, we're going to have to figure out what's the appropriate weighting between these two things, right? How do we actually pick the weighting between these two objective terms in order to really satisfy whatever we want to satisfy in terms of that second term? An alternative, though, would be to actually impose these as constraints. So you would say, well, if I know that in that second term, I'm really trying to make some residual, say, of an ODE equal to 0, then I can say, well, no, let's not put it in the objective and have to worry about a weighting. Let's actually impose it as a constraint and solve this constrained problem. Now, for those of you who are familiar, you might look at this and say, well, how am I going to solve this problem? Maybe I'm just going to take those constraints and throw them into the objective anyway. So what's so different? Well, what I'm going to be trying to advocate today is actually looking at this as a constraint problem and using specific algorithms for doing constrained optimization, which would be fundamentally different than just throwing this into the objective. But this is the motivation for bringing these in the first place. So you can sort of motivate this whole idea from different settings. I put physics-informed learning, FAIR, machine learning, but there's other kinds of settings too, not necessarily related to machine learning, simulation optimization, where you're trying to basically impose some additional constraints on your prediction function or whatever it is. There's a lot of challenges if you just think about it from the optimization side, where I come from in terms of like, how do you solve these kinds of problems? Well, just like in the unconstrained setting, there's a lot of questions that come in terms of having algorithms that have guaranteed convergence, complexity guarantees, stability guarantees, with respect to changes in the input. How well do these things generalize? There's also additional challenges that come in for constrained optimization, having to do with, first of all, what kinds of algorithms you're going to do. We'll try to avoid penalty type methods, as I mentioned before, and then also degeneracy and infeasibility. I'm not going to get too much into the weeds about like handling all of these different issues. I'm really just going to try to give you the overall idea of what the algorithms are, why they're different from just doing some kind of penalty approach, and then give you some additional convergence theory and things like that. So I'd like to just demonstrate for you first, though, just like why we're excited about this. So this is a very simple problem, very kind of a toy example of doing this kind of thing between basically data fitting and imposing, say, a solution of you want to solve basically an ODE. So this is a problem where you're trying to predict the movement of a spring. The orange data points are some observations that you have so far. So if you think about this as going left to right, this is time. Say you observed this, height of this spring over for a few time periods or 2 time points. And then you're trying to basically train a neural network that's going to predict the rest of the trajectory over time, okay? The green dots are points in space where you're essentially, when you're training, going to be imposing that you want the residual of the spring equation equal to 0. So that would be that second term of the objective before. Basically, you want that residual to be 0. On the left-hand side, the training is being done in this unconstrained way, where you just put that residual into the objective function with some weighting, and then you run some kind of stochastic gradient method on that. And you can see that, yes, it's working over time, but it's a little bit slow, especially in terms of that right-hand side of the predictions. Getting that accuracy takes a long time. On the right-hand side, what we did is we used one of our constrained optimization methods, and what we included was 3 constraints, not even all the green data points, but just 3 points in time imposing a constraint that says we want the residual of that spring equation to be 0. We run our constrained optimization algorithm on that, and what we can see is much faster convergence to what appears to be the correct prediction. So, and again, we're basically using the same kind of thing. We actually are including both of those terms in the objective, but we're just introducing these constraints and using a different type of algorithm and seeing much faster convergence or behavior towards getting a better prediction. And we want to explore this in terms of setting up the algorithms more generally and talking about their convergence and so forth. Okay, so let me tell you a little about the algorithms and how they're different from just sort of the unconstrained setting. So if you're familiar with unconstrained optimization using the stochastic gradient type method, this is going to be just a quick crash course in that. Generally, you're applying this to a function that you assume to be continuously differentiable with a Lipschitz gradient. The algorithm is very simple. You're basically iteratively taking steps in the negative gradient direction, but really you're using just approximations of the true gradient based on sampling your data or something like that. You would analyze the behavior of the algorithm, basically thinking about the stochastic process that's being defined by this method. And without getting too crazy in terms of all the details, you have to make some kind of assumptions. The assumptions are oftentimes, and you can loosen these, but oftentimes what you would see is that the first of these assumptions here is that your stochastic gradients are unbiased estimators of the true gradient, which is pretty easy to have in general. And then the second one is some kind of boundedness of a second moment kind of thing, or you can write it in terms of like a variance, bound on the variance of your stochastic estimate, right? But the convergence theory, like why does this work? Why does the stochastic gradient method work is very simple. It's just using a typical kind of upper bounding by a quadratic of your objective locally around any given point, giving you a bound that you can then, with under this assumption, say that the expected change in your function is bounded above by these 2 terms. And what this is that the term related to the true gradient squared with the alpha in front, this is like a step size, and then another term which has related to the noise and has the step size squared. And the fact that you have basically a good term, the decreased term with alpha, and the noise term with alpha squared is critical to saying that this could work. If you choose the alpha small enough, you can get the first term essentially to dominate the second one. And this is where you can talk about some nice behavior. So you can say things like, if I have a fixed step size that's sufficiently small, I can say that the expected average gradient in the long run is going to be bounded by something related to, Lipschitz constant and noise. And if I actually make the step sizes diminish at an appropriate rate, then I can say things like, in the limit of the expected gradient squared is going to be 0, or if I do further steps, this is 0. Almost sure the convergence is gradient to 0, something like that. Now, I want to go to the constrained setting. So that was just for the unconstrained setting using stochastic gradient, very now classical stuff. what if we want to end up solving some kind of constrained problems? Well, first thing I should mention is that, especially if you think about our constraints being defined by data, there's a lot of different paradigms for even modeling the constraints in the first place, what kind of constraints you could use. So you can imagine something like a constraint that says the expected value of something, some function needs to be 0. Or you can think about what are called robust optimization or probabilistic constraints. These end up with a lot of additional complications that we hope to be able to get to sometime. But for now, what I'm going to start with today is assuming we have constraints that are just, maybe a few of them that are, I would say, deterministic. Like we're just picking a subsample of data points, we're imposing these constraints. So unlike in the objective, where we're only going to assume we can get stochastic gradient estimates, for the constraints, we're going to assume we can evaluate the constraints themselves and the derivatives of them. That's going to be relevant when I talk about the algorithms in a second. First, I want to explain something about this idea of using a penalty method to do constrained optimization. So let's say you have a problem like this at the top. Minimize an objective function subject to some constraints, equalities and inequalities. You can say that there is some kind of equivalence between solving this constrained optimization problem and solving this unconstrained one, where you take this constraint functions, you turn it into some kind of violation function with some norm, and then you have a weighting term like this. So there is some kind of equivalence between these two problems. Where does that equivalence come from? Well, we don't need to get too much into the details, but if you make a pretty loose kinds of assumption about your problem, and one very loose type of assumption is called calmness. You basically would say that if the problem is calm, it has to do with sort of the growth of this function around a certain point, you can say that you have a penalty function that is exact. What exact means is that if you actually have a local minimizer of the constrained problem, if the problem itself is calm with respect to a norm around that point, then there exists a threshold for that lambda that says solving the constraint problem is equivalent to solving the penalty problem in the sense that the point x star, or minimizer of our constraint problem, is also going to be a local minimizer of this penalty function. So there, you can see now that at least in terms of their minimizers, there's some nice relationship for a penalty function versus the constraint problem itself. Me personally, I think people overemphasize the relevance of this kind of theory for practical use. They would say, okay, well, I can just throw it into the objective, I can minimize that function, everything is nice. Well, yes and no. I mean, exact penalization is really a theory about what happens at minimizers, and we're talking about it, over the entire space. There's not necessarily that behavior. So one thing you can see, for example, is that the constraint problem has a nice, well-defined solution, and the penalty function could even be unbounded below. Right? So it's really only about, what's happening at minimizers where this theory is relevant. I should also say that when you're talking about using stochastic algorithms, it makes it even less relevant, right? You're never even necessarily getting close, very, very close to a minimizer. And so it's just overall, the practical relevance of this theory sort of falls apart, in my opinion. So the point I'm trying to make is that there is a difference between the constrained problem and this sort of penalty type method. And using penalty methods to solve the constraint type problem, you really want to say, for example, like this residual that I'm putting in my objective, you really want it to be 0, formulating it as a constraint and using a constrained optimization algorithm can be much more effective. And I'll try to also explain that further with some pictures in a second. So let's now go to this constrained setting. Okay, so for the moment, let me just work with equality constraints. And actually, for the rest of the talk, I'm just going to focus on equality constraints. We can have some stuff on inequalities, but that's going to be a little bit messier. So let's just think about equality constraints. The framework that I'm going to be working in is called Newton SQP. It's very classical kind of stuff. You can formulate the algorithm itself in two types of ways. You can say, okay, I have my constraint problem. I can write down its first order optimality conditions. So, under some assumptions, these would be, it would be any solution x to this problem, there would exist a y that satisfies these equations. And then you can apply Newton's method in the x and y, the primal and we call primal and dual variables. And each iteration then would involve solving a linear system that looks like. Alternatively, you can think about this as your problem you're trying to solve. You set up a sub-problem based on basically Taylor expansions around your current iterate, and you solve this problem for the step D. And again, this, under assumptions about H, would lend you the same kind of system. So that's why we call it Newton SQP. It's kind of Newton's method in optimality conditions, quadratic approximation of the original problem that you're doing sequentially. That's what SQP name comes from. Let me try to show you with a picture about why this kind of method is fundamentally different than doing any kind of regularization or penalization or something like that. Imagine you've got your problem. This is a two-dimensional search space. Here's your constraint. So C of X. And imagine you're at some point xk. If all you do is take your objective function and the violation of your constraints, like the norm of C, into objective with some weighting, and then you would compute, say, a stochastic gradient of that F part, you could get any kind of step in this space, right? You could get steps that move away from the constraints towards the constraints, depending on the weighting that you're using, depending on the error in your gradient estimate, you could be moving all around here. But if you use this type of method, the key thing is that you're computing a search direction that is satisfying an affine approximation of your constraints. And so what that means is any step that you take is going to take you in some sense towards your feasible region, right? So, at your xk, you would have your function value and your Jacobian value here. There's an affine approximation of the constraint that you're getting from that. And no matter what gradient approximation or anything that you get from there, you're going to be moving towards this point. So there's putting this sort of, I don't know if you want to think about it like extra priority on your constraints, giving you fundamentally always a step that's going to move you towards those constraints. Another thing that would happen if you're actually at a feasible point is that your step would be in the null space, which again would keep you potentially from moving very far off. You could move off your constraint, but you would stay relatively close. So this would be the kind of algorithm that we would come up with from this. From here, there's still various things that you need to work out, like you compute your search directions this way. Where do your step sizes come from? And then overall, how would you show under what conditions you would actually solve the constrained problem here? There's going to be a lot that I'm going to sweep under the rug. The one thing I'm going to just briefly mention, but then sweep a lot of the details under the rug, is the fact that when you actually compute your directions this way, the step sizes that we come up with in our algorithm are based on trying to get descent and decrease then in a merit, where the merit function looks like this. Now, you might look at this and say, wait a second, you're going back to doing some kind of penalty method? Not exactly, because all we're using this for is in computing our step sizes. We're not actually trying to just directly take a descent step on this phi directly. We're still computing our directions this way. So it's still fundamentally different. But to prove or to come up with a full algorithm, you still need a step size, and you use the merit function for that. Very, very quickly, I'll explain to you that we essentially can show convergence behavior just like you would for stochastic gradient in the unconstrained case. So if you remember, the key inequality that you saw for the unconstrained case looked like this. There was the nice decreased term and then something coming from the noise. Again, we have the same kind of thing here, but now in our merit function. There's a lot of different complications that I'm skipping over that have to do with this tau and so forth. But just this inequality here, you're basically getting decrease on the order of something that's related to an optimality measure. I'll get back to that in the next slide. And then these two end up being noisy. So basically, you can get, with appropriate step sizes, it's going to be our betas here. I'll go back in a second. There's a beta on the top there. So you're basically playing around with that in order to say you're getting a nice term in terms of decreasing your phi and then something related to the noise. So if you choose the step sizes appropriately, like a constant step size or a diminishing step size, you get very similar kinds of results like you would for the unconstrained. And this part I wrote in terms of delta Q, but then you can follow up and say, all right, you've got your stationarity measure for your constrained problem. Remember when I was talking about applying Newton's method and basically on equations that look like this. So we can say that we're getting, an expectation or basically convergence in probability of these measures to zero, right? Yeah, so this script T is this, I didn't really put it there. there ends up being sort of an adaptive update for this tau parameter, which is your value there. And you use that in your step size. And so a lot of the complications, and this comes from SQP, unison in the deterministic case. In the deterministic case, when things are nice, you can show that by certain rules for decreasing this tau, you eventually get it stable and it's fixed. In the stochastic setting, this is a lot messier kind of stuff. So we have to basically say that under some nice behavior, we get convergence guarantee, but there's additional complications too, like if that adaptive update of the tau ends up falling apart. But what we show under different assumptions is that basically this event that I'm defining here, that it ends up being bounded below by a constant, essentially occurs with probability 1. There's just, the bad behavior, if you've got like small tails of your distribution, your stochastic gradient, things can be nice. I'm kind of sweeping that away. All right. So again, and the key observation here is because we're working with these constraints that are not random or anything like that, everything, so basically our search directions end up being still unbiased estimates of what we would have gotten if we had the true gradients, and that's what makes all of the analysis kind of nice, just like the unconstrained case. All right. So, okay, from this point on, you've seen now what is our kind of core algorithm. Like everything that I'm going to be saying going forward is sort of based on that, that kind of method. Here I'm showing some additional experiments. Probably don't need to go to too much detail here. Again, this was on a much larger set of test problems comparing our stochastic SQP approach with some kind of stochastic subgradient method where we just use soft constraint. Basically, what we're showing here is for different noise levels, how the stochastic SQP is able to bring down the feasibility error much more than the stochastic subgradient method, even if you tune your penalty parameter that you're using for that. And again, in terms of optimality, you see nice behavior. Yeah. From there, from that sort of core algorithmic idea, we have since done various kinds of extensions that I'll just briefly mention. Okay, so one thing, and I actually talked about this yesterday here, is that we can take that algorithm and actually prove stronger convergence guarantees. So what I showed so far was basically saying that we're solving the constraint problem with, the iterates are somehow, converging in probability, or at least the stationarity measure is going to 0 in probability. You can show almost sure convergence guarantees. We have a paper on that. And that also talks about the convergence of Lagrange multiplier estimates. We've also looked at a different type of algorithm where we relax certain constraint qualifications. So one thing that we have here is we have to assume that the Jacobians of these constraint matrices have full rank, and this is a typical thing for constrained optimization. We showed worst case complexity guarantees of this algorithm. We showed that we can generalize this to problems with inequality constraints as well. We've done a little bit of work on interior point methods. One thing that often comes up is the question of, well, when you're running your algorithm, you have to solve a linear system that if I'm thinking about, training a huge neural network or something like this, how am I solving those linear systems? It seems very expensive. Well, first of all, if you don't have many constraints, then you can do what's called the step decomposition method, and it doesn't actually require that much extra work. Another thing you can do is use iterative solvers to solve that linear system inexactly with just a few matrix vector products. And we can still show an algorithm that has convergence guarantees in that setting as well. We've done some other work for the inequality constraint case where we focus on active set identification. And again, that was something I mentioned in the talk yesterday. What I'd like to briefly mention for the rest of the talk today is tell you about going from this sort of core algorithm to using momentum methods. And this is momentum for constraint optimization that I'll get to here. But before I go further on, maybe I should just stop for a second and see if anybody has any questions so far, or if everything seems good so far. Sure. Essentially, And this, again, it goes to sort of classical textbook stuff for constrained optimization. You're trying to figure out, basically the algorithm is computing steps in a certain way. This is where your DK function is. But to figure out how far to move, you have to have sort of a measure of progress. Like what is, when I look at a particular next iterate, is it better than my previous one? One way to do that is with this kind of merit function. The problem with this kind of merit function is that you don't know in advance what's an appropriate weighting of your objective and your constraint. So you could look at a point and say, well, if the tau, for example, is too big, it might actually not really be taking you closer to a solution. So what was typically done is that there's these different rules for changing this tau to recognize, like, oh, based on this step that I computed here, it seems like my current tau is not putting enough weight on minimizing constraint bias. And so what I should actually do is decrease it, so that if you trust this is the step that you're trusting, you sort of adjust your weighting based on that. And then you can, if you decrease the tau, your direction will be a descent direction, merit function. And then there's some, like I mentioned before, some nice theory from that, like under reasonable, pretty nice assumptions. Then eventually this tau will settle down at some fixed value and then becomes like consistent, sort of, just like an exact penalty function theory, consistent between. But you have to adaptively figure that out. Diminish it. Well, that's the thing that so you don't want it to converge to zero. If it converges to zero, then essentially you're going to be ignoring, you're not optimizing. So in certain degenerate cases, like if your constrained optimization problem is degenerate in some way, then the tau going to zero can happen. Right? But what is, if the problem is not degenerate, then you want to be able to say that it will eventually settle down at some positive constant value, and then you're essentially having an algorithm that is minimizing this function in this direction. Mm-hmm. Yeah, so in the paper, the original paper we had, there's more flexibility with this. One thing you should point out, this looks very much like like a 1 over Lipschitz constant type step size, right? Where you're going to use the beta to control whether it stays fixed. We have some more complicated rules for choosing the step size. One reason we do that is because we know about the constraints explicitly. If you're trying to decrease, like if you just were focusing on this second part, you actually can compute those values and do something like a line search. You don't really want to do a line search on the full function because that would require you evaluating your objective, which you don't necessarily want to do. We have basically a way of trying to be a little bit more aggressive than this for your step sizes. But I just didn't want to put too many help. Okay. So that's the sort of core algorithm. And what we thought to do recently was to extend this to using momentum, because people have obviously found that in the unconstrained setting, momentum can improve performance a lot. And so what and also beyond just simple momentum, you could also have what I would refer to as diagonal scaling methods like Adagrad, Armas, Prop, and Atom. They're particularly effective. You can motivate these in various ways. So what we wanted to do was to see if we can extend those kinds of guarantees from the unconstrained setting to our Newton SQP type framework. We have been able to do that to get basically comparable guarantees like you see in certain unconstrained setting. And so I just want to sort of introduce those and explain to you what that all looks like. So if you're familiar, if you think about I'm going to talk about two methods, the heavy ball method and Atom, okay? So in the unconstrained setting, so heavy ball method basically looks like this. You're in stochastic heavy ball. You compute a gradient estimate just like in stochastic gradient method. But then you're going to do this sort of rolling, weighted average in your previous. And there's different, motivation about why you use momentum. You can, probably the easiest way is to think about it. You've got this like ill-conditioned, say, quadratic function. A gradient method trying to go to a minimizer would bounce back and forth and do a lot of extra this way. Whereas if you average those gradients, it'll sort of push you more in the direction towards the minimizer more quickly. In non-convex settings, there's probably other kinds of motivations for using momentum. In any case, it seems to work very well, be very effective. And the algorithm is stated here for the unconstrained case. For us, we wanted to figure out first how to apply this in the constrained setting. And then, so where exactly the momentum should be applied. And then, can we prove convergence guarantees comparable to what we see for stochastic heavy ball? So let's go back again to our constrained setting. So we have the problem with equality constraints at the top. I'll remind you of the first order conditions. And another way to write these optimality conditions is what we have here. If you think about what's going on here, essentially, this is saying that the gradient is basically in the range of the Jacobian transpose here. Another way of thinking about this same condition is that the projection of the gradient onto the null space of the Jacobian has to be 0. So you basically have a feasible point where the projection of the gradient is going to be 0, okay, where the projection is written this way. And in terms of the SQP method, the way that the algorithm is, that I said to you before, really that direction that we're computing has two components to it. One component that is essentially moving towards the constraints. You remember I had that linearization from our here. There's basically any step that you compute is like a step towards that affine approximation and then a step in the null space. So there's a component in the range and then a component in the null space. Thinking about those two things, we can then apply momentum in this constrained setting. We don't want to actually apply it in terms of this step towards the constraint. Okay, but what we do want to do is impose it on the step that's in the null space. So overall, if you were to take this V and U and not do anything related to momentum, just add these two pieces together, this would be the same V that I mentioned in the previous kind of algorithm. So it would just be the basic addition of this step here, which is essentially in the range space going towards the constraints, and then a step in the null space where this here is the projected gradient. So our method here to apply momentum, we're going to apply the momentum to this null space component. You can see here we're basically taking now a running average of these U's, and then our D becomes the step towards the constraints and then the projection of this R onto the null space. So this is now, we have to do this extra projection because we're doing this rolling average of R's, and actually the null space itself is changing from iteration to iteration. So this would be, the basic idea of the algorithm, and it turns out both for our theory and actually for the performance of the algorithm, the fact that we apply momentum to the projected gradients and not the gradients themselves ends up being hugely important. So I would say that the intuition is, to me anyway, is that like if you look at a particular iteration, like it's a particular point that you're at, right, right. And so, and also, I lost my train of thought. What I'm trying to say is that you really shouldn't be, because your gradient, whatever effect you have on your gradient from the fact that there's noise, it really isn't affecting this component of it. And so even if you're just trying to, well, I don't know, I mean, like, even if you're thinking about the algorithm without any kind of average, what's happening in the null space is really what's happening towards optimality. optimality. And what you're trying to do with momentum is affect what's happening as your steps towards optimality. Imagine you're just sort of in the null space. Let me have like your constraints are just affine constraints, and every step you're taking is just in the null space. You really just want to isolate this averaging to the null space. Exactly. Yeah. I think this is exactly the intuition. What we weren't sure of is whether you could, sort of show guarantees in both cases. But in fact, what we've seen so far is we're only really able to show guarantees in this case. And again, this extra projection is critical too, because when you use averaging, you even have, the fact that the null space is changing every time is also an important fact. So in any case, we're applying the momentum in these projected gradients, not the full ones. I think that, what I can do very briefly is just say, okay, here's some very basic assumptions about the problem. This is an assumption about the stochastic gradients. And again, we can loosen them a little bit to really talk about them being unbiased in the null spaces. And then some bounded. In this case, it's a little bit of a simpler assumption we have here on this the second one, but it's very similar to the previous one, essentially a bound on the variance of the stochastic gradient estimates. And then this is the kind of guarantee that one can show. It looks a little bit messy. We're essentially showing what's happening with our the expected value of this composition here of the projected gradient squared and the norm of the constraint violation. Showing that it is bounded above by this, so if you run k iterations, it's bounded above by this here. What then becomes a little bit tricky is to understand that this upper bound, you can essentially choose parameters to make this as small as you want, right? So this C, by the way, which comes from obviously dependent on the parameter beta of the algorithm, the beta you're choosing for the heavy ball method. We tried to make it a little bit more flexible. This H min and H max or some additional. This is what this HK here just sort of added in an additional scalar term. As long as it's bounded by an interval, then things are fine. So overall, we have this upper bound, and from here you can basically see that if you choose alpha small enough, so this term here is the constant. Once you choose the beta, this becomes a constant. You can then make this term as small as you want by choosing a small alpha, and then by doing a different, so that term affects here, but then with additional more iterations, you can make this term as small as you want. So overall, you can, obviously, if you want to, your real practical performance, you may be limited by the number of iterations you actually want to do, but at least in theory, you can make this bound as small as you want. The other thing that we have is a version of Atom here. This turns out to be a slightly different than the original Atom algorithm in terms of the bias correction. You end up having a term here that makes this step size in front monotonic. But this comes from a paper by Francis Bach and others where they showed that this is sort of comparable to the original Atom in terms of its practical performance, and it makes the analysis somewhat more straightforward. So that's the one we were working with here. Again, this is the original Atom for the unconstrained case. For the constrained case, we're going to do a very similar thing like we did for the heavy ball method, where we're going to be computing our stochastic gradient. We have our step constraints. We're applying this momentum for these, what you call the tangential steps in the null space. First momentum, second momentum, bias correction, and then try to show the convergence guarantees from here. We borrowed a lot from this paper, as I mentioned, of Bach and others. One additional thing that comes up beyond the heavy ball cases, you have to make somewhat of a stronger assumption on the noise. It's still relatively loose here. This is basically the last one in red. This epsilon that you see at the end is the one that actually appears in the algorithm itself. Okay, so it's regularized the second term. Long story short, we end up with a very, very long and complicated expression for this upper bound again. But again, it's something that you can show can be as small as desired. So we're showing here at the end the sort of long-run average, the expected value of this projected gradient and the constraint violation bounded above like this. We then explain in our paper, which again is coming out probably very next few days, that with a sequential choice of the parameters of the algorithm, you can make each of these terms as small as you want. Okay, at least in theory. So we do see that this has a nice effect in terms of practical behavior. So I'm going to show you a couple examples here, or at least one. I forget if I put both in. Examples of some physics-informed learning or learning with respect to knowing certain ODEs. So as I was saying before, you have basically this is a setting where you're trying to learn, you're trying to train a neural network to learn the mapping of between some parameters of let's say a PDE and a solution. Okay, and generally what you could do is basically minimize the sum of two terms. One of them we're trying to essentially make the residual equal to 0 of your PDE, and the other one is more like a data fitting term. We, just like I was explaining before with the spring equation, you would basically have these two terms in your objective, but you would also impose some additional equality constraints saying you know exactly that the residual should be 0, and you impose those as constraints, and you run our SQP type algorithm. So I think I just have maybe this one. The labels here made a little bit small. The blue here is Adam for just doing the unconstrained problem, so no constraint. This orange one, so that's the one here. This orange one is doing Adam. We're doing like in our SQP kind of context, but by applying the momentum to the full gradient, not the projected. That's this orange one here. The green one is heavy ball. Okay, not so great in general for this one. But the last one is our SQP app. So the last algorithm that's the red. So these are the losses for either full batch or mini batch, different step size choices for that same problem that I showed you before about predicting the movement of a spring. So it's a very simple problem, but you can clearly see the SQP atom version of it. You're getting the losses to decrease much better just by imposing these simple constraints. Oh, yeah, I didn't put the constraint violation here. That's a good point. Right, so that you could think about it like for our constraints that we're imposing, we're basically selecting a few of the terms that are in the original. So like, the full loss has it over all larger set of data. So it's still kind of buried in here, the constraint violation. It's essentially just a way that we see it as a way of just accelerating the algorithm to diminish that residual term. Yeah. Exactly. Exactly. It's just kind of, I don't know if bootstrapping is the right term, but you're just kind of pushing it towards those things. I mean, basically, what you could see for, if you're just thinking about the residuals, there's a lot of different, well, I don't know. I mean, this is just, I think, not only accelerating the satisfaction of those few terms that you impose as constraints, but the rest of them as well. And oh yeah, I did put one more in here. This is another basically trying to learn the mapping that would give you the solution of 2D flow equations. They're written here. This is a more interesting problem because what we're trying to do here is learn or train a neural network to learn the solution, but for different values of this diffusion coefficient. So we actually train the model by having various different inputs here. Okay, so they're just basically some 0, 1 grid here. And so we're trying to be able to train the model so that given any input, we can predict the output, right? So this is an example of what once we train the model, if you actually have a certain diffusion coefficient and you look at what the true solution is, we can compare that to what our model will predict. So this is much more complicated than just a single spring trajectory. This is a little bit less distinct here, but we do find that we're running additional papers not out yet. But we do see that, okay, heavy balls not so great, there's these different versions of Atom, but with our version of Atom, we're able to get lower losses. And I think if we were to, we're sort of tweaking also the way that we're setting up this problem to see sort of better solutions. And overall, we're seeing this kind of improvement. It's a little bit less obviously than the spring one, but at least we're seeing something here. So, okay, conclusion. I tried to motivate for you, first of all, why we even think about constrained optimization in the context of supervised learning. Another one that I didn't talk about here is in the context of fair learning, which is like if you want to impose a certain limit on unfairness of your predictions, you can do that with a hard constraint. And we have other papers about the behaviors of the algorithm there, which are also very nice. So I tried to motivate that in the first place. I tried to talk about this stochastic gradient-based SQP type methods. There's various extensions that we have other papers on that I didn't talk about today. The one that I did talk about in terms of momentum methods will be out again soon. And just some references for you there. And I think I'll stop and take any questions if you have them. Thanks for your attention. That's what we found in the few problems, at least, that we saw. Yeah, and I think that's pretty widely seen. Yeah. Yeah. Well, it turns out to be there's a lot of similarities in the analysis, and so and even some parts of the analysis of the heavy ball ends up being useful for atoms. So it makes sense to kind of put them together, as we have them in the paper. But when you go to the actual experiments, the atom one is, generally, much better. Yeah. Yeah, so well, actually, in these experiments, when we're doing it with equalities only, we didn't end up really using in any of our experiments we didn't use second derivatives in all the constraints. You could put them there, but we didn't end up using them a lot. We did have some work on interior point methods, and one thing you would have for that H would be the Hessian of the barrier part. But generally, we wrote the papers and did the analysis for some general H as long as it remains bounded, but so far in our experiments, we don't play around too much with that. We found, instead, better behavior by just looking at these, the atom variants. Calmness? Oh, okay, yeah. This one.
So I'm wondering, how do we check the
Oh, not really easy question. Yeah. I mean, I'm sure there's various settings where you could do it if you know something about the solution. Could be, okay. I don't know, actually. That's I'm sure you would have much more to say about that than I do. This is it's just a known sort of very weak, relatively weak assumption that where you can talk about exactness of the penalty function. That's all. There are certain, more common ones that you can verify, like LICQ, MICQ. These are constraint qualifications that would then imply that imply calmness. But calmness itself is weaker than that.
So
I mean, I wouldn't say that it is a constraint qualification because it's sort of weaker than those, but it is at least sufficient for this exact penalty. Yeah. Yeah, so the inequality one is first of all, it's much more difficult to think about constrained optimization with inequalities because it has now a combinatorial aspect to it. If you only have a few algorithmically, you can, essentially, still make it efficient. But if you have many, many inequality constraints, essentially what you would need to do for an SQP setting is solve a QP to get your direction, which can be very expensive. And this is part of the reason why we also looked at interior point methods. Long story short, the inequality cases still needs a lot, there's more work to do, but we do have some previous papers on that.